They are barely 1,000 light-years across, yet they shine like galaxies 10 times larger, and we see them when the universe is less than 5% of its current age. Astronomers call them little red dots, compact, intensely red objects in James Webb's deep fields that should be rare, but instead show up again and again. To understand why they're so weird, we need to unpack what little, red, and bright really mean in cosmology. Size, color, and luminosity are not just aesthetic labels. They encode mass, temperature, distance, and time. And when we decode those three properties for these objects, they do not fit comfortably inside our standard picture of how galaxies grow. First, little. When JWST looks at a distant galaxy, it can't see individual stars. It sees a fuzzy blob. The apparent size of that blob on the sky, combined with the distance, tells us the physical size. For many of these red dots, that size is a few hundred to maybe 1,000 light-years across. For comparison, the Milky Way's stellar disk is about 100,000 light-years wide. So these things are like packing the mass of a major galaxy into a region only 1% as large. Now, red. Light from distant galaxies is stretched, or redshifted, by the expansion of the universe. The farther away, and therefore the earlier in cosmic time, the galaxy is, the more its light is shifted toward longer wavelengths. JWST is tuned to infrared, which is perfect for catching this stretched ancient light. But there are two ways an object can look red to JWST. One is cosmological redshift. The whole spectrum is shifted. The other is intrinsic redness. The object actually emits more infrared than visible light, for example, because it's full of cool stars or shrouded in dust. For little red dots, both effects seem to be at play. Their spectra, how bright they are at different wavelengths, suggest very high redshifts, often between 7 and 12. That means we're seeing them when the universe is only 300 to 700 million years old. On top of that, their light looks reddened, as if dust is absorbing the bluer photons and letting the redder ones through. Dust is made of heavy elements like carbon, silicon, and iron. Those elements are forged in stars and supernovae, so a dusty object that early implies a lot of previous star formation has already happened. Then there is bright. Some of these compact sources have luminosities comparable to or exceeding the Milky Way. Luminosity is energy output per second. To get that much light, you either need a huge number of stars, very massive and hot stars, or a central engine like a feeding supermassive black hole. When astronomers fit models to the light from these red dots, they often infer stellar masses of tens to hundreds of billions of suns, crammed into that tiny volume and assembled in just a few 100 million years of cosmic history. That is the core of the puzzle. In the standard LAP CDM cosmology, lambda-cold dark matter, structure grows hierarchically. Tiny dark matter halos form first, then merge and accrete gas, slowly building up larger galaxies over billions of years. Simulations like Illustrist NG and FIRE do produce early galaxies, but typically they are smaller, less massive, and less chemically enriched than what these little red dots seem to require. It's as if you walked into a nursery and found a fully grown adult who claims to be 3 months old. So what could these objects actually be? One possibility is that they are extremely compact starburst galaxies. In this picture, gas collapses very efficiently into the center of a dark matter halo, triggering an intense, short-lived burst of star formation. The stars form so densely that supernovae and stellar winds quickly blow out or heat the remaining gas, quenching further growth. You end up with a small, massive, red and dead galaxy, surprisingly early in cosmic time. Some models predict such systems, but the number JWST sees may be higher than expected. Another option is that many little red dots are not dominated by stars at all, but by actively feeding black holes, quasars in miniature. A black hole accretion disk can outshine its host galaxy, especially if the galaxy is small. If the accretion region is compact and surrounded by dusty gas, the light can be both extremely bright and very red. In that case, we might be overestimating the stellar mass, because we're assuming starlight when a lot of the energy is actually coming from matter spiraling into a black hole. Distinguishing between these scenarios requires spectroscopy, splitting the light into fine wavelength bins and looking for diagnostic features. Starlight imprinted with gas clouds produces sharp emission and absorption lines from elements like hydrogen, oxygen, and nitrogen. Accretion disks and jets have different line ratios and broader line shapes because the gas is moving at thousands of kilometers per second. JWST's NIR spec instrument has started to collect such spectra, and the early hints are mixed. Some little red dots show strong star formation signatures, others look more like buried active galactic nuclei. There's also the possibility that we are being fooled by gravitational lensing. Massive foreground galaxies or clusters can bend and magnify the light of background objects, making them appear brighter and sometimes more compact. Lensing is a well-known effect. Hubble's famous Einstein rings are examples. If a significant fraction of little red dots are lensed, their intrinsic luminosities and sizes would be more modest. But careful lens modeling suggests that while lensing explains some cases, it cannot account for all of them. Too many red dots appear in regions without obvious massive lenses. We also have to consider the assumptions baked into our models when we convert light into mass. For example, we usually assume a particular initial mass function, a distribution of stellar masses at birth. If early galaxies formed proportionally more massive stars than we expect, they could produce a lot of light and heavy elements quickly, without needing as much total mass. A top-heavy initial mass function would change how we interpret these red dots and might reduce the tension with LEM-CDM, but it would also ripple through many other areas of astrophysics, from reionization to supernova rates. Finally, there is the uncomfortable possibility that our cosmological parameters, or even our basic framework, might need adjustment. If, for instance, the amplitude of small-scale density fluctuations in the early universe was slightly higher than we think, structure could collapse faster, making massive early galaxies more common. Or, if dark matter has properties beyond being cold and collisionless, say, self-interactions or a warm component, the timing and efficiency of galaxy formation could shift. Most cosmologists are cautious here. The data are still young, and extraordinary claims require extraordinary evidence. But the little red dots are one of the sharpest current stress tests of our cosmic story. In the coming years, deeper JWST surveys, longer exposures, and more spectra will refine distances, reveal dynamics, and map chemical abundances in these compact objects. Radio and submillimeter telescopes like ALMA will measure their cold gas and dust, telling us how much raw material for future stars they still hold. Either we will discover that clever astrophysics, starbursts, black holes, lensing, and revised stellar populations can fully explain them, or we will be forced to admit that our picture of how quickly the universe can build complexity is incomplete. Because if these little red dots are real, massive, and as common as they currently appear, then they are not just curiosities in JWST images, they are signposts pointing toward a universe that learned to grow up much faster than we ever imagined. And they are only the first hint of even stranger early cosmic monsters waiting in the data.